就做。好，那我们今天很荣幸邀请到交通大学的特聘教授简仁宗教授来我们莅临本系来演讲。那简仁宗教授他是机器学习还有语音处理方面的知名学者，他曾经在许多单位，譬如说Microsoft Research Asia， 还有 IBM TJ Watson Research Center 等等相当知名的国际研究机构进行访问研究。那今天他要演讲的主题topic model 是现在非常热门的一种，也是非常有用一种研究一种这个机器学习的模型，那它可以用在像是 Web 的 mining 或是语音的信号处理方面。那我们现在就把时间交给简仁宗教授，谢谢。
Suppose we have a foreigner student here, so show display. I think you can speak Chinese. So maybe I present English, but show display to all the audience. Yeah. In this coming hour, I would like to share some studies. We published some papers on this area, on these topics entitled Unsupervised Learning Bio-topic Models. Why I go to this title, actually I present this this talk in several occasions. I presented this talk in some workshop on big data and machine learning in Jiao Tong University. I also presented some talk in Tsinghua University. I recently presented this talk in several places, including I just presented a tutorial in ISCSLP, International Symposium on Chinese Spoken Language Processing, also on this topic. But today's talk is only half of my presented tutorial. I just take the first half, which is more tutorial style, more survey about how to build topic models. What's the solution to this model? When we go to these topics, I will first introduce topic model in general. This is very general approach to different applications in information engineering area. I will talk some applications, some concepts, and motivations why we go to this topic model. And then I will in today's talk I will talk about how to find solution to topic models, including some approximate inference using variation inference, keep sampling. And then I talk about some extensions of topic model to different issues, different applications in the end. For the second part, I skip. I only go to the first part. Finally, I will make a conclusion. First of all, what is topic model? How we apply topic model to the application on hand? Think about abundant data. From, for example, library. We have many articles, many documents in books, in our archive, right? They are all words, right? Similar to the data in web, but in web mining, what you observe is all text data. We have a lot of text data. We want to find some tool to analyze this abundant data. So what is the challenge? Yeah, the challenge is we have abundant data. We have so much data, so many data, in our system. And also, I not only talk about text. The data can be any kinds of technical data. Including speech, including image, video, social data, and so on and so forth. You can imagine, for example, Google. You can retrieve any kinds of pictures, right? Image or speech. You can input speech and retrieve any data, not only text, also different kinds of technical data. And how the Google researchers build a Google system. You can imagine they collect a lot of data from internet. Those data are very, what we say, noisy, or we say heterogeneous, or ear-post. That means some data are very ambiguous. Even in text, we have very ambiguous data. In any kind of conversation, in any kind of, for example, in BBS, any text you type in are very heterogeneous. That means, the data are not so organized. You need to model your data carefully so that you can extract some information. You can build some useful application. And then you can see about the model we want to build maybe not so right. I mean, the assumption error may happen in our model construction. Maybe overtrain, maybe undertrain. We may have too many data, but the model parameters are not so many. So how to build a model which can reflect your data as better as possible. This is the way we want to go. And not only the training data we model, we want to have a better prediction. So for example, in my course I teach machine learning in Jiao Tong University. I always tell my students we are not only dealing with training data, more important, we need to have better prediction. So how can we have better prediction? This is our concern. So we need to have some tool to deal with these issues. These tools should could be used to analyze or even search, recognize or understand the real data we collect. And the model should faithfully reflect uncertainty, and should reflect a noise condition. And the model should be adaptive, should be scalable, and it should be robust. You can imagine you have more data, you need to build a more complex model. You have small data, you use a simple model. So the model should be adaptive. And how to represent this model structure, how to represent this uncertainty. It's data based on the tool. Here is a kind of probability. We use a prior distribution or even prior process to represent some prior information. However, the model we train, is shown in title. I'm talking about unsupervised learning. We don't have ground truth. We only have abundant data. We want to find some latent variables, latent semantics, in documents, in data. So no ground truth. So we want to build data. This is how we say unsupervised learning. Unsupervised， 非监督式学习。OK， 好，就是说问问题可以用中文哈，我是比正我是用英文哈。How can we identify? How can we find out these latent variables? Or we say latent topics or latent themes. It's the topic model we are. This is the goal topic model would like to achieve. So, given if we train such kind of latent models, we can annotate data, document. It's a text document, spoken document, even it's any kind of document. We can do annotation, and then we can do retrievals given this annotation, and then we can predict and do search summarization. So in the beginning, start from the scratch. How we can build a topic model? We have suppose we collect a lot of data. We put in the bag. In this bag, we have many words. The words may happen many times for some words. For many other words may happen very rarely, just one time or two times. But anyway, we have a bag of words. What we can do before in information retrieval, the simplest model is to, for example, based on language model, we will just count unigram, bigram, trigram, right? And based on these probabilities, we calculate how relevant the query relevant to some specific document. So we want to score, find which document give you a highest score, so that you can retrieve the document you want. So how can we do this scoring? A language model is just a very simple approach. A better way is to go to topic model. Try to explore not only the information in the text lexicon level, I mean the word level, but also some latent topics which are embedded, which are behind the data you don't observe. Some latent, you want to extract these latent variables, to know what's the semantics in your data, in your document. How to do that? How to find a latent variable? Before going to this latent variable, we need to know the basic probability model. In topic model, we basically we model, for example, text, words, model documents. So all these variables are binomials. We have for example, we have k topics. So you have k states for this topic in your data. For example, in your words, we need to define a dictionary, and the size of a dictionary, for example, tens of thousands of words in your dictionary. Then all the words happening in your dictionary is a kind of probability. You can calculate this multinomial distribution. Multinomial, we say probability. But when we introduce latent topics, it becomes a multinomial Mitchell model. The Mitchell here means topics. I show you some example later. In the beginning, what is multinomial? Yeah, for example, if you have three states, the multinomial calculate this ratio, which is maximum likelihood to achieve the highest likelihood for multinomial variable. But in multinomial Mitchell model, we will have multiple topics, multiple Mitchell components in observation in your data. Suppose we have several worm. 1, 2, 3, 4, 5, 6, 7. We have 7 worm. Each worm, data may happen in each worm. Each worm here may represent topics. So each worm will be relevant to different topics in your model. Some topics may have a higher probability. Some topics may have a lower probability, which are reflected by the size of the circles in this figure. So you can see, if we want to find some variable, here is in terms of color. We calculate probability of random variable here is color, which is a summation, which you need to consider all the observation given different on. On here represent topics. We need to consider the world happening in different topics. Then we need to multiply this by the probability of topics so that we can calculate the probability for this random variable. So in this sense, we can imagine if we want to represent some data, for example, newspaper. We have a newspaper. We have many words in, for example, sports. For some, politics, right, and there's some other kinds of news. Health, something else. And the different category, can be represented as a different kind of topics. So how we represent this data? We represent each word under different topics. Finally, we can calculate the likelihood for all the words in the documents. Here is newspaper. So if we consider this multinomial distribution, the topics, for example, we have 3 topics. All the possible topics are all inside these 3 topics. So it's under a kind of topic simplex. The probability of topics, what will happen in this simplex, or below this simplex and above this original point. You can imagine, for example, we have a document here. It's an abstract from some scientific article. And then we have different words inside this document, this abstract. And then finally, we find out, for example, we show 4 topics shown in different colors. And each word may happen in each topics. But some words may happen in some topic very frequently, but some words may happen in some topic very rarely. How this situation happens depends on the model you train from topic models. So suppose the words are listed in this column are the, we say, topic words, which are the frequent words. I mean high probability. So we can Yeah, we can know the physical meaning under some topics by looking at the topic words. Yeah, for example, here talking about some gene, yeah, friend, number, DNA, right? Yeah, this talk about some design processing method, computer, right? So they represent some semantics in some kind of latent topics. Why I say latent topic? Because they are not true topics. They are the latent topic we find from data. So it's called latent. So representing a word using the probability, yeah, it's a summation over all the word given different topics, sum up over all the topics. So each word, yeah, will be represented here. I show the highest topic. So different words are represented by different topics. And the different topics may have different, we say, topic proportion, which means how likely this topic happen in your document. Some topics may happen very frequent. Some topic may happen very rarely. Depends on the length, depends on the probability we train from a topic model, yeah, which is a parameter in topic model. Here it's an example showing different words under different topics. Yeah, the length here show how the words related to the topics. The longer means the more relevant to this topic. Some words are not shown, means these words are not so relevant to this topic. The probability is very, very close to zero, so we don't show the bar here. Yeah, this can click in this. You can see. This is trained from some database. Yeah, the more. Interesting example here. For example, we have data from, for example, Wikipedia. Yeah, we like to go to Wikipedia to find some information, right? And so you type in some keyword, and then you can pick up some document show some information about this word. So you can imagine in Wikipedia we have many documents for different words, right? So this is the observation. We can use topic model. Yeah, basically we have some observation, we have some latent variable. I want to show you how this model is built, how this model is trained from training data. Basically, we need to achieve some optimization and finding model parameters which give you some probabilities to tell you how the topics happen and how the relevance between topics and the words. Yeah, this example I will show you later. Okay. In the final. This can be accessed in internet. But I would like to show you before this. This link. I want to talk about some other applications. Which also apply topic model. To analyze data. For example, speech. Speech. How speech data can be modeled by topic models. You can imagine, for example, we have speech signals. The signals here, for each time frame, we may check some features. Given some features, we may have some code book, and then we can quantize different features using different code words. This code book, these code words, these labels corresponding to some multinomial observations. So it comes out some acoustic words, yeah, representing speech waveforms. Yeah, and those are discrete, represented by multinomials. So given these sequential multinomial variables, yeah, we can find some latent topics, yeah, underlying those observations. For example, we have 4 topics shown in different colors, and each word under different topics, yeah, have some different probabilities. For example, the word in this segment is more related to these topics. The word in this segment is more related to these topics. So different relation between words and topic can be shown by the parameters we train from topic model. So basically, the parameters in topic model are some kind of probabilities, or even some hyperparameter which can use to draw these probabilities to represent your observations. Here, it's not so clear, but I just want to show you for some song, different songs may have different labels. The label can be artificially defined, can be also automatically estimated. If we automatically estimate these labels, yeah, we can use a topic model to find this latent information, even from sound. Not only speech, sound can be, for example, you step the door, it's a kind of sound. If you have an airplane, it's also an airplane sound, it's also a kind of sound. Yeah, we have different kind of sound. We can classify, we can we can do a kind of clustering over the sounds, over the data we observe. Topic model give you an organized way, yeah, which can eject some latent variables, so that we can model data in a better way. Even you can think about this is a spectrogram for speech signal. This axis is time frame, and this is frequency. You can imagine this spectrogram is a kind of image. Although this signal represents some speech signal, but if you look at this as a 2-dimensional data, actually it's an image. So what topic model can do is to find some latent information given this observation. So we can see we have data not only in time domain but also in frequency domain. So we want to eject some latent variable z from time and the frequency data. So data is not only 1-dimensional, it's 2-dimensional data. We can maximize some likelihood and finally estimate this topic model. Yeah, but before estimating, we need to define the number of topics. Then we can estimate topic information from topic model. Even in image, we can do annotation. We observe some photos, images. We don't know ground truth. We want to find some latent information inside the image. The latent information may represent people there, some rock, some tree, some sky. Right? But we don't have ground truth. We just want to find some clustering. Yeah, given your data. Right? Topic model can represent this kind of image data. even we can apply for image understanding. You can imagine once we know how to find data information from image, then you can see we have different data topics that given some image. And this data you put together, you can understand given this data topic. So if you go beyond topic level, you can understand in a high level given different topics for this data. So we can know more. I mean we can understand better given this topic information. Even we can apply for scene modeling. Yeah, we can check some very fundamental basis, or it's a kind of topics, yeah, which represent image, so that we can do matching. We can retrieve the image data in your application. So this is the application. So in what follows, I'm talking about how to build, how to estimate a topic model. I don't want to show too many mathematics. Yeah, mathematics are not the most important thing in your research, but I want to tell you the concept, the tool, which you can apply to your research. I want to inspire you to think about how topic model can build for your problem, for your applications. So this is my purpose. So in the following models, we can see topic models can be realized in different ways to deal with different issues in real world problems. But basically, the highest citations if you type in topic model, the highest with this LDA latent rich allocation has the highest citations. But before LDA, actually there are some topic model presented before, and also in recent years we have more topic models proposed to deal with a more complicated problem. I don't have time to show too complicated model, but I will talk more about LDA and show you how to how to estimate this model. So that you can modify this model for your problem. This is my purpose in this talk. So the topic model starts from LSA. What is LSA? The earliest topic model was proposed for information retrieval. Based on this, we say SVD, singular variable decomposition, which is very popular in linear algebra, which is used to decompose a matrix. Here, matrix is the data. For example, we have many words happening in many documents, and we count the number of occurrences given this data. And the topic model here, for example, we set totally we have R topics. So we decompose this non-square matrix into 3 submatrix. This is an approximation. It's not exact. Anyway, minimizing some error and find out this decomposition. In the middle part of this matrix is diagonal matrix the diagonal terms represent some topics. For example, we have 10 topics. The value for this in this matrix represent the magnitude of the energy of the topic in your data. And we have the other two matrices, which represent word space and the document space based on some topics. This is the earliest topic model in literature. Then in 1999, Hoffman modified this topic model into a probabilistic solution, building all the observation in terms of probabilities, so that we can represent uncertainties in using probabilities. So all the terms here are represented in probabilities. Here Z is latent topics, W is words, D is document. And this we are maximizing the joint distribution of word and the document, and finding latent topic Z, which is represented by these two parameters. This is the word probability given some topics. This is topic probability given some document. So the parameters are represented by these probabilities. The most popular model is called LDA. Proposed in 2003, almost more than 10 years ago. But still, this research is still a kind of a main track in machine learning conferences, including ICML and the NIPS. If you attend these two main conferences in machine learning, you can find some sessions entitled by topic models. So although it's already 10 years old, more than 10 years old, but it's still very, the research space is still very large. You can explore some idea from this direction. Anyway, LDA is an extension from PLSA. It's I try to deal with some data. This model is quite general. Can be used to represent seen data and also unseen data, so that you can have better prediction to predict some words which are unseen in your training data. The trick is to introduce a prime. This is the multinomial for this latent variable. We say topic proportion. The key trick is to introduce a Dirichlet. So we say latent Dirichlet allocation. We introduce a Dirichlet prime with hyperparameter alpha. To represent this multinomial parameter. And then, given this multinomial parameter, we can draw some latent topics to determine the words in your observation. And the words are represented by some word distribution given by some topics represented by this beta. And these are the variables in this topic model. So you can imagine in this problem, the difficulty is we introduce not only one latent variable. Actually, Z is the label topics. This is latent variable. Theta is the topic proportion. This is probability. In this model, this is also latent variable. So we have two latent variables. So different from PLSA, this is more complicated, with more latent variables. How can we solve this problem? And finally, find model parameters. Here are alpha and beta. Yeah, this is the solution to topic model based on LDN. How to do that? This slide just show you how this variable related to the data, related to the proportion, related to the topic words. These observations represent different words in an article. Here represent topic. For example, we have 3 topics. So this is topic index. This is topic proportion. Yeah. Actually, here we have many topics. So the length show the amount of the importance for this topic related to this corpus. So this is theta represent this, and the alpha is some hyperparameter. Yeah, beta is some parameter. Yeah, representing the word given topics. So we want to solve this problem. So we need to define some probability to construct this model. Yeah, here are multinomial probability, Dirichlet distribution, and so on and so forth. So how to solve this problem? Yeah, we need to go to some tools. These tools here, mainly I show you variation inference and the Gibbs sampling. What's the concept, idea for these 2 inference solutions? I know many of you are not so clear about this tool because these are included in machine learning course. I believe many of you first time see these terms in this talk. So you may not catch very well. If you don't catch very well, this is not your fault. It's my fault. It's because we don't have too much time to explain how this theory explain this, how the model is constructed based on this theory. I don't want to go too much on the detail of theory. I just want to show you some motivation why we go to this inference and what's the trick to this inference and to find solution to the model. Yeah, this is what I want to deliver to you. First of all, you can think about we collect data. We just want to maximize some likelihood given some parameters. We want to the parameter I show here. For example, parameter alpha, beta, or eta. These are all including in theta here. We want to maximize likelihood. Likelihood is calculated from data under this latent variable, and we want to finally we want to find alpha and the beta, or alpha and the eta. So we need to maximize some probability. Here we maximize this likelihood, and then we find theta. But this likelihood cannot define without latent variable, because this is the model we assume. So we need to consider all the possible latent variables in likelihood function. But the estimation of parameters given this latent variable could not solve in a kind of exact solution. This should be solved in the so-called EM algorithm. This is very, very important algorithm in machine learning. This shows you how to estimate parameters. Because we have latent variable, we have something unseen, something missing. How can we maximize? We need to start from an initial value. Even some initial value. We build this latent model, then we maximize this likelihood given the initial value you have, then you update your parameter from theta 1 to theta 2. Then given the new parameter theta 2, we maximize the latent variable, keep the likelihood given latent variable. Then you update parameter from theta 2 to theta 3. So the estimation should be done iteratively because of this latent variable happening in this model. And here, just show you the mathematics about this EM algorithm. I don't go to this detail. I just show you in EM algorithm, we have 2 steps. The first step is to find some expectation. Here, expectation are trying to find some posterior probability Q, which is closest to the true posterior probability. Give you the KL divergence to be 0. So that given this approximate distribution, we maximize lower bound for the